Okay, this segment is about pairs of angles. So we're working with pairs, pairs, there we go, of angles. And today we're going to hit three major types of pairs. We're going to talk about complementary angles, supplementary angles, and vertical angles. Okay, so that's it. That's our three types. We're going to take them one at a time here, and we'll go from there. Okay, so complementary angles are pretty straightforward. If I have two angles, let's say I have one here that measures, let's say, 60 degrees, and I have another angle here that measures 30 degrees. Then if the sum of these angles, so let's call this angle B, call this angle D, if the measure of these angles, the measure of angle B plus the measure of angle D is equal to 90, so the key number here is 90, then I have complementary angles. Note, the two angles don't have to be touching each other, they just have to be two angles whose measures add up to 90 degrees. Supplementary angles are very similar. Now I might have one that is 60 degrees, and I might have another angle that is 120 degrees. Okay, so let's call this the measure, let's call that P, let's call that T, and if I have the measure of angle P plus the measure of angle T is equal to 180, 60 and 120 adds up to 180, then I say these are supplementary. Okay, so that ultimately they have to add up to 180. Now note, they're not near each other. In fact, later on we're going to see that if I have two angles that are next to each other that do this, 60 and 120, that's going to form a line, and we would call this a linear pair. But that's coming down the road. Supplementary just means that if I add them, I get 180. Okay, vertical angles Okay, so the vertical here is actually a reference to the vertex. So vertical angles actually means across the vertex. Does not mean anything going up and down. It's just across the vertex. Vertical angles are formed when you cross two lines. Okay, so if I take the intersection of two lines, I get the vertex of a whole bunch of angles right there. The angles that are across the vertex from each other, the ones whose sides form opposite rays, those are what we call vertical angles. So this one and this one is a pair of vertical angles. Also, this angle here and the one down here is also called a vertical angle. Now, if I take a quick observation there, it appears that these angles, the vertical angles, the two green ones, or the two orange ones, are the same size. Now, that's something that we're going to reach for here in a second, but just as a quick observation at this point. Okay, so in order to prove that vertical angles are the same size, we're going to need a couple of things along the way. We're going to need one called the angle addition postulate. which says that if I have an angle, let's call it AOC, and I have some point B in the interior, not necessarily the center, but the interior of that angle, then if I add this measure to that measure, I get the measure of the whole thing. So this is going to say that the measure of angle AOB plus the measure of angle BOC has got to equal to the measure of angle AOC. Now there's a special case of this where AOC is a straight angle, also known as a line, and if B lies on one side of this, right, not only does it add up to angle AOC, but the measure of angle AOB plus the measure of angle BOC should add up to 180. So when you have this linear pair, they in fact add up to 180 degrees. Sometimes this special case is what we refer to as the linear pair postulate, but we're going to take it as a special case of the angle addition postulate because that's what your book does. Okay, so when you have an equivalence relationships, there's certain properties. So there's a set of properties of all equivalence relationships. Okay, one is what we call the reflexive property. And that just says that everything is equal to itself. That seems pretty straightforward. One is called a symmetric property, which says that if something is equal to something else, so if A is equal to B, then you can write this backwards. B has to equal A. Kind of useful, again, fairly obvious. And finally, there's a transitive property, okay, which says if A is equal to B and B is equal to C, then logically A is equal to C. So if we have some sort of relationship that has a sense of equivalence, all three of these, the reflexive, the symmetric, and the transitive property, need to be true. Okay, so we're building a set of properties with this angle addition postulate, this set of equivalence properties, reflexive, symmetric, transitive, that we're going to use to prove some other stuff. We need a couple more, so hang on, we're going to get them next. Okay, so there's a couple of other properties that we need at this point. One is what we're going to call the addition property, which is something that you already know from algebra, so this is kind of reviewy. But if A is equal to B and C is equal to D, then A minus C, or A plus addition, A plus C should equal B plus D. This essentially says that if I have something that's equal to something else, I can add one to one side of the equation, one to the other, and it does not change the fact that things are equal. Basically, you're adding the same thing to both sides of the equation. If you can add to both sides of the equation, you can also subtract. So we have a subtraction property. Okay, so in a subtraction property, again, we have A equal to B, and we have C equal to D. Then this time we're going to say if I subtract C from one side and D from the other side, the equation still holds. It basically says if I subtract the same thing from both sides, I'm good to go. And finally, you have a substitution property. Okay, so what does a substitution property say? Alright, so if A equals B, then in an equation, or even an inequality, you can replace one for the other. So you can take out the A and you can put in the B and vice versa. Okay, so we've been doing some building up here to something that's called the vertical angle theorem. Okay, which just states that vertical angles are congruent. Now, that seems pretty straightforward. What we're saying is that if I have two lines that cross each other, and I call this angle 1 and I call this angle 2, then those two angles have to be congruent to each other. Now, this is a theorem. It's not a postulate. It's not something that's supposedly obvious. It's something that we actually have to prove. Okay, so when I go to prove this, I'm going to be given certain information. I know that angle 1 and angle 2 are in fact vertical. Okay, so they lie across from each other. What I want to prove is that angle 1 is congruent to angle 2. So I know this is the first time that we're actually doing a proof in this class, and that's okay. Okay, usually when we make a proof in this class, we're going to make a little table. One side of the table, we're going to make statements. And on the other side of the table, we're going to give reasons, or we're going to explain why that statement can be there. So the first statement that I have is that angle 1 and the measure of angle 1 plus the measure of angle, and I'm going to interject an angle 3 in here, have to equal 180. Well, I know that because of what we said before, the angle addition postulate. So if I look, these two angles, this one here and this one here, form a linear pair, which means all total, they have to add up to 180 degrees. Likewise, I can do the same thing with measure of angle 2 and the measure of angle 3. They also have to equal 180. Okay, so 2 and 3 also have to be a little bit adding up to 180 by the angle addition postulate. All right, so number 2. We can say now that since both of these are equal to 180, we can write that the measure of angle 1 plus the measure of angle 3 is equal to the measure of angle 2 plus the measure of angle 3. Okay, why can I do that? Because they're both equal to 180. So I can take out this 180 and I could substitute that in. I use the substitution property. Okay, number 3. Well, they both have an angle 3 involved here. So I can subtract that from both sides of the equation and get back that the measure of angle, well, first off, I know that the measure of angle 3 has to equal itself. Aha, because that's my reflexive property, right? And then finally, I can subtract that from both sides of the equation. Measure of angle 1 is then equal to the measure of angle 2, which means angle 1 is congruent to angle 2. What did I do there? I subtracted. This is the subtraction property. And I have now proven what I set out to prove, that angle 1 is equal to angle 2, or congruent. So we now know that this theorem is true. Okay, so once I've proven that, I don't have to prove it anymore. I know this is true. I can use it for all time. Okay, so a quick summary of ideas. We have that complementary angles add up to 90. We know that supplementary angles add up to 180. If they happen to be next to each other, we call them a linear pair. And we've also learned that if I have two crossing lines, these are what are called vertical angles. And these are, in fact, going to be congruent. So if I call this angle 1 and angle 2, Angle 1 is congruent to angle 2. They have the same size. Okay, so this is by the vertical angle theorem, which we'll be using later in this class. So there's a bit of a summary for you, and that's where we wanted to get to today.